definition of a circle is the set of all points. So here's all my points, and you know this is an infinite number of points going around here that are equally distant from the center. So this is the center, and the equal distance length is the radius. Pretend that is a straight line. Okay, and as I go around the circle, like kind of like the hands of a clock, it's perfect. Like it's the same distance all the way around. Okay, and the radius is the distance from the center of a circle to any point on the circle. So the line of a circle is not really a line because lines are straight, and this is a set of infinite points. Basically, it's the set of all of the points that are equally distant from that point right there. Okay, and that distance is the radius. If we go back to before, term A, we talked about the distance. If you take the distance formula, okay, if the center would be like, say, x1, y1, which we normally call hk when we're talking about circles. Don't know why, we just do. And then a point on the circle would be x2, y2, then the radius would equal d from the distance formula. Okay, so if you ever have to figure out the distance of a circle and you know the center and you know a point, then you can find the radius. Sure, I'm going to go ahead and put it on here. The standard equation of a circle, just to remind you, we're not going to be using these right now, but just, you know, is x minus h squared plus y minus k squared is equal to r squared, where h, k, and r are numbers. And x and y stay x and y. Okay, so no car troubles. Okay, so we've got circles, right? Congruent circles are circles with congruent radii. Radii is the plural of radius. We don't say radiuses, it's radii. So if we have this circle here and we have this circle here and we want to know, are these circles congruent? The radii have to be the same length. So circle A and circle B, they would be congruent because I marked that their radii are the same length. Okay. Chord is a segment that joins 2 points on a circle. Now it is any 2 points on the circle. So it can go from here to here. That's a chord. We can have a chord that goes straight through the center of the circle, which has a special name, which we'll talk about in a second, that you probably already know. You know, it can... You'll remember in a sec. So it's any segment that joins 2 points on the circle. I mean, it can be really small. It's just any segment. Take 2 points on the circle, connect the dots, you have a chord. Makes contact at a single point on the circle. So it touches the circle, but it does not intersect the circle like a secant line does. Like the secant line cuts into the circle, the tangent sort of just bumps up against it as it goes by. which is kind of like when we were talking about if you go off on a tangent, like usually when you're going off on a tangent, it kind of touches on what you were originally talking about and then veers off to the left or right or whatever. So tangent lines sort of do that also. There. It was perfect when I moved it. There. So the tangent line is touching the circle at one single point. Okay, so the line and the point, or in the circle, share one point in common. The point of tangency is the point where the line touches the circle. So this point right here is the point of tangency. Okay, next we can have inscribed polygons and circumscribed polygons. Inscribed is easy to remember because it's inside the circle, inscribed. And the vertices are all points on the circle. So any polygon, triangle, square, any polygon at all that is inside of a circle with the vertices touching the circle is inscribed. Okay, so vertices on circle is very important. A circumscribed, oh, this one is not drawn very well. A circumscribed polygon goes around the outside of the circle, and then the circle touches tangent, like it has tangent line basically to each edge of the polygon. So we have points of tangency along the circle, and you will have the same number of points of tangency as there are sides on the polygon. So if we have a circle inside a triangle, circumscribed, so it's going to be touching that, you'll have 3 tangent points. If it's inside a square, you'll have 4 tangent points. Pentagon, 5, etc. Not too bad. Then it's not inscribed. Yeah, it has to be all of the vertices of the polygon are touching for it to be technically called inscribed. If you had like a circle, let's say, and you had some triangle in it, but only one vertice was touching it, it's just a triangle sitting in a circle, but it's not an inscribed triangle. For it to be inscribed, all 3 vertices would have to be touching. So I should put that all vertices. And the same thing, like if I have a circle inside a polygon like here and it's only touching in one spot or 2 spots, it's not touching all of the sides of the polygon, then it's not circumscribed. The circle has to be tangent to all the sides of the polygon, or the polygon's vertices all have to touch the circle. Concentric circles are 2 circles in the same plane with the same center. So if I have, like if this is circle A and this is circle B, both A and B have a center at N. Okay. So you have expanding radii. Because the radius of A is going to be greater than the radius of B. And you can have concentric circles that go out, 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 out. In nature, the most common concentric circle is like if you drip water and then you get rings. Yeah, the ripples are not perfect circles, but the center is where the water dripped, and then the radiating circles out are concentric. And this... No, because of things that are in the water. You know, if the water was like completely pure H2O with nothing in it, and then you had it in like a vacuum environment where air and things like that aren't going to affect the movement, and then drop, it would be perfect. But because you've got air resistance and you've got, you know, weeds and things in the water in the bottom, it all affects the movement of the water, so they're not perfect. Perfect doesn't really happen in nature all that often unless you're talking about Fibonacci spirals. Those are perfect and they happen in nature. Okay, a sphere is like a circle, but instead of being all the points from the center that go on a flat plane, it's all the points in the center that go from in space, three-dimensional. So we have a radius, and if we have here, that R is going to be the same as if I have it coming up here to touch that R. We're going over there to touch that R. They're all going to be the same distance everywhere around the center. Bubbles form almost perfect spheres. Again, though, not quite perfect because the soap tends to like pool at the bottom, and so it pulls it a little off of perfect. Okay, circle. What are we going to call the circle? Hold on. We name the circle by its center, so that's circle A. We have radii AB, AC, and AD. Our diameter, we only have one diameter. It is BD because it's the only line that goes through the center. Our chords are BD, because remember diameter is a chord, and BE. Our secant line is line N, and our tangent line is line M. If line N is tangent to the circle, what's the point of tangency? We want to be able to identify that. Anybody? Yes, B. So that just the point where that line touches the circle is B. No. No, that's simple. If OC is 12, so OC is a radius, and it's 12, what is the longest possible chord that exists? 24, right? Because the longest possible chord is always going to be the diameter. Nothing can be longer than the diameter because it goes across the widest part of the circle, and so it would be 24. Okay, and then we have a triangle that is inscribed in the circle. No, we don't. Yeah, but it doesn't touch the, yeah, it doesn't touch the outside. No, here. If I connect those, now name me a triangle that is inscribed in the circle. OBC, yeah. Yeah, OEC wouldn't be inscribed because it's not, O is not touching the edge, but not OBC, EBC. EBC. But here we have a triangle that's touching all of the edges, so let me fix that so that when we go back to look at it later, it makes sense. Okay. All right, any questions on that? So if a line is perpendicular to a radius at a point on the circle, then that line is tangent to the circle. There is no way to have...
there's no way to not have a line that's perpendicular to the radius and touch the circle at all.
Right, exactly. There's no way to have a tangent line that is not perpendicular to a radius. Because if I draw this radius over here, I'm not even touching the line. Okay, so it's going to be perpendicular to the radius at that point where it touches the tangent line. Okay, so anytime you have a radius touching the tangent line, it will be a 90-degree angle. That's what you need to get from there. Okay. Then we have if a line is tangent to the circle, then it is perpendicular to the radius at the point of tangency. So we have, if a line is perpendicular to the radius, it's tangent. And then if a line is tangent, then it's perpendicular. It's the two sides of the same coin, basically. So radius perpendicular to the tangent line at the point of tangency, that's what you need to know. Now here we have, if I take two tangent lines, okay, and they intersect at some point off of the circle, but they're both tangent to the circle, so they are tangent to the circle, and you know, in theory maybe these lines keep going and going. If we take the segment between the 2 points of tangency to that point where the two tangent lines cross, these segments are congruent. So this length is the same as that length. So far okay? And of course these would be the same because these are radii. So those are already the same no matter what. Good? Okay. Here we have, answer the following. I didn't put the question in here. Okay, there. Now I have the question. Right. Here we have a tangent line. Here's my radius. My radius is 5. My tangent line segment is 12. What do I know about when the radius touches the tangent line? It's a 90-degree angle. And so I can use that information to find MK because I have a right triangle. So I can use the Pythagorean theorem. So this would be C. So I'd have 25 plus 144 is equal to C squared. So I'd have 169 is equal to C squared. And so then C would be 13. So that is MK is 13. If AC, AC is 23, how long is BC? 23. Okay, if ACB, this whole thing is 38, what do you think BCO is? Half of 38, exactly. And that will be 19. Okay, because what we get here is we get this, these two are congruent, these two are congruent, and if you cut through here, you get congruent triangles. So they're, yeah, it's a not a median really because this isn't a triangle. But you get two congruent triangles. What you get is an angle bisector. Okay, and then we have some tangent circles here, some tangent lines to two circles. If NM is 8 and MK is 4 and JM is 10, we want to find ML. What do you think is happening with these two triangles? Well, I can tell right here. This is 90 degrees and this is 90 degrees, right? And this angle is going to be the same as this angle, which means this angle will be the same as this angle, so I have similar triangles. So we can do the ratios. So 4 over 10 is going to be, sorry, 4 over x, or question mark, whatever, is going to be the same as 8 over 10. I can do that way. Yeah. Right, 4 and 8. No, because see how the right angle, so 8 and 4 go together. Yeah, 4 over 8 is equal to x over 10. Because 4 and 8 are both on this side of the triangle, the right angle. So I get 8x equals 40. So x, which is LM, is going to be 5, or ML, whatever. So far okay? And then if I relabel those with red for this problem, Jn is 16, Kl is 8, and Nk, this whole long thing between there and there, is 45. And I want to find this part of it. Okay? Yeah. Okay. CD is tangent to both A and B. And then A and B are tangent to each other because they're sharing one point. If AD is 16 and BC is 9, we want to find CD. Okay. Well, ready? We're using radii, right? If this is 16, this is also 16. And if this is 9, this is also 9. And isn't this length the same as this length?
Right.
25. So we make a rectangle. Does that make sense? All right, not assigned on this one, but it's a cool drawing. Okay, an arc is any continuous part of a circle. So when we take a circle, so like any circle, should do highlight. Any part of the circle, that's an arc. An arc can be all the way around, like the whole circle pretty much. Just any continuous part of a circle is an arc. Okay, the central angle is an angle whose vertex is at the center of a circle. So if I have a circle and I draw an angle from the center, this is a central angle. And it can be any size between 1 and 359 degrees. Usually, though, we only measure the ones under 180. So I would say between 1 and 180. Actually, it doesn't even have to be 1, but okay, I'll just put 0 and 180. But greater than, because maybe we have like a half angle, half degree. Any questions on those? Is an arc of a circle whose endpoints are on the diameter. So it's a half circle. So semicircle means half circle. So if I take a circle and I come in with a diameter, I get 2 semicircles. One semicircle here, one semicircle here. Okay. A minor arc is any arc that is smaller than half a circle. Okay, so we talk about minor arcs. Yeah, it's an arc, but it's an arc. It's an arc that is from any size in here. Like it can't be bigger. It doesn't even equal a semicircle. It's smaller than a semicircle, and that's a minor arc. So it's going to be less than half a circle. Because remember I said an arc can be pretty much any size. So the minor arcs are less than half a circle. On the opposite end of that, a major arc is larger than a semicircle. So bigger than a half circle. So if I come in with a circle, and here's the halfway point, the major arc is going to be, at minimum, like that big. It's got to be bigger than a half circle. And it can go anywhere from, here to maybe there, you know, around, just like a little piece that's missing. Congruent arcs are arcs that are the same length, arcs with equal measure. And we'll talk in a second about how we measure the arc. But these arcs are the same length. Arcs are same length. Okay, so 2 semicircles are congruent arcs. I'm not going to try to draw arcs of the same length. It's not going to work. One postulate and one theorem. Arc addition postulate is if you take 2 arcs and they're right next to each other. The length of the first arc plus the length of the second arc equals the length of the total arcs. So if I have a circle and I have one arc here and I have one arc here, my new arc is equal to the whole thing. So blue equals red plus green. See, so this arc plus this arc equals the whole arc. And you can go the opposite way too. If I take an arc and I break it into pieces, the lengths of the 2 new arcs are like, you subtract one from the big one and you get the third one. Easy enough, yes? Okay. Then we have, in a circle, congruent minor arcs have congruent chords and congruent central angles. Okay, now this is where I'm going to talk to you about the measure of an arc. Okay. If we have, I'm just going to come through and do that, okay, and pretend that is the center of the circle even though it is not. Okay, this is the center. Okay. And I have a blue arc here and I have a red arc here. Okay. The red and blue are congruent. Okay. I'm going to call this point A and this point B and this point C and this point D. And if I come in and I draw chords, AB and DC, AB will be congruent to DC. And then if I label these angles like angle 1 and angle 2, angle 1 will be congruent to angle 2. One postulate, one theorem. So what we have is, if these arcs are congruent, then the chords connecting the arcs, so the ends of the arcs are congruent, and then the angles, the central angles to the arcs are also congruent. Now, an arc gets measured by the central angle, which I'm going to, on the next page, have a nice picture for that. But so the length of the blue arc is the same as angle 1. And the length of the red arc is the same as angle 2. Arcs are measured in degrees, just like angles, because circles are measured in degrees. So far okay? So here we go. If I have AOB, that's this angle here, that is going to form this arc. So this angle is 120 degrees, so is the arc. And the symbol for an arc is to have just a little, like an arc over top of your letters. And the M in front, so this is the measure of angle AOB is equal to the measure of arc AB. Okay, now a minor arc, you use 2 letters. But the major arc, you need to use 3 letters, because if I use AB again, I'm talking about this side over here. If I'm talking about the major arc, so it's bigger than a semicircle, I use another letter over here so that you're talking about going all the way around. So we have red for this one, and then we'll do blue for the major arc, and the major arc is ACB, and the angle AOB is 240, so the major arc ACB is also 240.
So all you gotta do is determine the angle.
You just determine the angle and you know the length of the arc. And of course, angles can be measured with protractors. So you don't have to try to like take a flexible ruler and measure the curve. Like we don't have to know the length in that way. The length is the degrees. That's how we talk about them. Now you can calculate the actual length of this using the circumference formula of a circle and all that stuff. We can do that, but we don't need to. We'll just talk about it in terms of degrees. Okay, so semicircles are named with 3 points. So we have semicircle X, W, Z, and semicircle X, Y, Z. Okay, so semicircles and arcs. You need 3 letters. Okay, so, sorry, major arcs. Okay, minor arcs, you only need 2 letters. Okay. If I have the measure of arc WX plus the measure of arc XY, this is that addition thing, is equal to the measure of WY. Make sense? I take the 2 small ones and it makes the big one. And then if we have XY plus is congruent to YZ, then we have the chords that are congruent, which we talked about already. And then if the chord XY is congruent to the chord YZ, then that means the arcs are congruent. Okay, so congruent chords make congruent arcs, and congruent arcs make congruent chords. I don't know why I'm having such a hard time spelling arc. Okay, so far okay? We're almost done, I promise. Okay, here we go. LM is tangent to Q, so that makes this 90 degrees. And I want to find the arc length of LN. Well, if this is 90 and this is 24, a triangle adds up to 180. So I take 180 minus 90, which gives me 90, minus 24, which is 66 degrees. So here's 66 degrees. So LN, the measure of LN, the arc, is also 66 degrees. Not too bad? So as long as you know the angle, you know the arc length. So you just have to find the angle. Okay. So BC, that one's easy. BC, 41. Okay, BCD is going to take a little bit more work, but no, it's not actually, because it's a semicircle. It's going to be 180, because it said BCD, so it's the whole semicircle, right? Half a circle is 180, so here we go. We're half a circle right there. BCD.
Oh, okay.
Yeah. Now, if we went DBC, we're coming all the way around on this side. So we have a 41, a 90, and a 90. So that's 180 plus 41. So that's going to be 221. And then DC is just this little bit that's left. There's your 139. Not too bad? Okay, so for homework. That's an H. You want to do pages 57 58 and 59 odds. And again, don't forget you can do evens for extra credit.